మీరు 3, 2, 1 చెప్పండి. We start. Yeah. Good morning, my dear students. On this 6th day of our physics booster classes, today we'll be dealing with two important subtopics in the 2 years physics. One is by name, transmission of heat, and the other one is kinetic theory of gases. Both the topics are scoring. They have limited models there. Once your fundamentals are good and you have the practice of basic questions, highly scoreable, around 8 marks you are likely to get. Okay, I'm sure you will concentrate on the class and get benefited, please. The first topic we are going to start with is transmission of heat. Almost 2-3 formula only are there as far as this transmission of heat fundamentals are concerned. Under the heading of conduction there, suppose this is an iron rod. This is any metallic rod, which is a good conductor. One end of the conductor is maintained at a higher temperature, theta H. Theta H stands for higher temperature. Other end is kept at lower temperature. For example, it is kept in ice there at a theta low. Because of the temperature difference, heat energy will start flowing from higher temperature to low temperature. Let us say that in a time interval of T, let the quantity of heat energy flowing from higher temperature to lower temperature is Q. In a time interval T, how much heat energy is transported from higher temperature to low temperature means Q. Then L stands for length of the conductor. Okay, in other wordings there, L is the length of the conductor or length of the heat path. The heat will be traveling along this path. L is the length of the conductor or length of the heat path. Through what cross-section area this heat energy is flowing means that is A. Now, if the radius is R, the cross-section area comes out to be pi r square. Okay, these are the basic terms generally we are well equipped with. The first important term is about temperature difference. Always here in this topic, temperature difference means high temperature minus lower temperature, theta high minus theta low. What about temperature gradient? Whenever gradient is there, the distance term or length term will come to the denominator. Temperature gradient is nothing but delta theta by L. Okay, I want to know in a time interval T, how much quantity of heat energy is being transported from high temperature to low temperature. That Q is given by Ka delta theta T by L, the quantity of heat energy transported. Then comes the next important wording, heat current. You know that in current electricity, I stand for current. Here, a similar wording and a similar things will be there. The heat current is given by Q by T. There in current electricity, current means quantity of charge flowing by time. Here, heat current is the quantity of heat energy transported per unit time. So when you bring T to the denominator, Q by T comes to be Ka delta theta by L. Okay. Whenever the heat current is flowing through this particular conductor, the conductor will oppose the flow of heat. It offers some resistance called as thermal resistance. The thermal resistance and its reciprocal is thermal conductance. How thermal conductance is being defined as? Thermal conductance is basically defined as the quantity of heat energy transported per unit temperature difference per unit time, Q by delta theta T. If you write E delta theta by T to this side there, you get Ka by L. Okay, so this is the first point about the thermal conductance. Reciprocal of conductance is known as resistance there, and thermal resistance is 1 by G, and it comes to be L by Ka. So very frequently we had to use these points there. Okay. Most of the questions that come in the exam are based on the conductors being connected in series and parallel. Okay, you know the meaning of series combination. Conductors are connected end to end. This is one conductor, to this end one more conductor, to this end one more conductor. This is end-to-end connection. Okay, now when different conductors are connected in series there, naturally, whatever quantity of heat energy flowing, the same quantity of heat energy flow from one end to the other end. So in the series combination there, the quantity of heat energy as well as the heat current denoted by I will remain constant. The moment you hear the term series, in no time you have to write the point that the heat current I is constant, I is Q by T constant. Okay. Let the temperature difference across the first conductor is delta theta 1, that across second is delta theta 2, and delta theta 3 is the temperature difference across third. What is the effective conductor? Instead of having so many conductors to make the heat current to flow from one end to other end, you can replace all these conductors by a single effective conductor. Instead of using 3 different conductors to allow the current from one end to the other end, replace them by effective substitution, that is known as the series one. So what is the K effective in series? Means is this is a series conductor there. This series conductor is also connected in the same set of endpoints there, same set of endpoints. So what is the L effective in series means L1 plus L2 plus L3, and across this effective conductor, this is delta theta net. What are all the points we want here there? So if our short notes be better, something like this. So first thing in series combination is the heat current will remain constant, and delta theta net is nothing but delta theta 1 plus delta theta 2 plus delta theta 3. Just like electricity, RS is equal to effective thermal resistance in series is R1 plus R2 plus R3. And we can easily derive that. How to calculate this Ks means the L net divided by Ks. For this combined conductor, L net by Ks is L1 by K1 plus L2 by K2 plus L3 by K3. Okay, so whenever you want to calculate what is the effective coefficient of thermal conductivity in series combination means L net, where L net is nothing but L1 plus L2 plus L3 divided by Ks is L1 by K1 plus L2 by K2 plus L3 by K3. Coming to parallel combination. In parallel combination, the main feature need to be different conductors are connected between the same temperature difference. Suppose here one end at theta high and other end at theta L for first conductor. For every conductor, same thing. Here the temperature difference across first conductor theta high minus theta low. Second is also same, and even the effective one also same. Okay. In parallel combination, whatever heat energy comes, the heat energy will divide into 2 parts. Okay, if there are 2 conductors, 2 parts, n number of conductors, n part. So whatever heat energy is coming, it is dividing into 2 parts there. So the first and foremost point in parallel combination is they have to be connected in the same set of points, and temperature difference need to be constant across any conductor. Delta theta is constant. Whatever Q net comes, that will divide into different parts there. Suppose there are 3 conductors, I am writing Q net is Q1 plus Q2 plus Q3. Similarly, whatever heat current comes, that will divide into different parts. I net is I1 plus I2 plus I3. And what is the effective thermal resistance in parallel? Just like current electricity, 1 by Rp is 1 by R1 plus 1 by R2 plus 1 by R3. Here the additional point we have to remember is what is the effective coefficient of thermal conductivity in parallel. So all these conductors, when you replace by effective conductor, what is the effective coefficient of thermal conductivity in parallel? That Kp comes out to be K1A1 plus K2A2 plus K3A3 divided by A1 plus A2 plus A3. Okay. Generally, examiners interested about some special case, 2 conductors of same dimensions. That means length is same, area is same, but materials are different. Dimensions are same, length same, area same, materials different. In such a case, there effective coefficient of thermal conductivity in series combination comes out to be 2K1 K2 by K1 plus K2. It can be derived from these things, but time doesn't allow us to do that much in the exam. So we have to remember Ks is 2K1 K2 by K1 plus K2, and Kp comes out to be K1 plus K2 by 2. But strictly we have to understand that this is applicable when the dimensions are same, both are having same length, same area, and exactly 2 conductors. We are going to have the application of these things first. Yeah. The first simple bit is for 2 conductors of same dimensions. Just now we were discussing about that situation. For 2 conductors of same dimensions, but of coefficient of thermal conductivity is K1, K2, effective thermal conductivity in series combination is, and effective thermal conductivity in parallel combination is same. Okay, their Ks and Kp are same. That's what being given there. I want to know what the ratio between their individual thermal conductivities. Okay, if you recollect the formulae from the previous sheets there, this is Ks is given as Kp. Just now we have seen for 2 conductors of very same dimensions, and having thermal conductivity is K1, K2, Ks comes out to be 2 K1, K2 divided by K1 plus K2. What about Kp formula there? So K1 plus K2 divided by 2. Even though you remember that formula, most of you there, just I want to show you that particular thing there. Okay, for two conductors in series and parallel, this is what we use there. Then say, now the thing is 100% the school algebra. Okay, we need to do it. Then say, if you do cross multiplication, here it comes out to be K1 plus K2 whole square when you cross multiply is equal to 4K1 K2. Okay, but we want to know what is K1 by K2. Then this is a plus b whole square. As everyone knows, this comes out to be K1 square plus K2 square plus 2K1 K2 is equal to 4K1 K2. How do you solve any quadratic equation in general? On the right side, we need to have 0. So that particular small point makes us to get the idea that this 4K1 K2 should be brought towards the left, Okay, so here it comes out to be K1 square plus K2 square. 2K1 K2 minus 4K1 K2 comes out to be minus 2K1 K2 is 0. Everyone can notice that this is of the shape a square plus b square minus 2ab. What is a square plus b square minus 2ab? A minus b whole square. So based on that, this is K1 minus K2 whole square is 0. Take a simple square root there. So simple square root means K1 minus K2 is 0. It means if you bring this side, K1 is K2. So both K1, K2 are same. So when once they are same there, what the ratio between K1, K2 means? They are one and the same now, 1:1. That will be the answer for the question. K1 by K2 is 1, 1:1. Okay. From two conductors, we are going for three conductors. As is being little expected, the exam slightly need to be of higher standard there. Most probably. That is a simple and humble expectation only, of course. Then say, so from two conductors, when they switch over to the three conductors there, then for three conductors of very same dimensions, K1 is to K2 is to K3 is given as 3 is to 2 is to 6. When they are connected in series, Ks is given this much. Now I want to know, if they are connected in parallel, what will be the value of Kp there? So this is the question here. Okay, to begin with, first, K1 is to K2 is to K3 is given as 3 is to 2 is to 6. So I need not tell you that K1, we take it as 3K. So K2 is equal to 2K and K3 is equal to 6K because their simple ratio is 3 is to 2 is to 6. He has given the details about Ks there. Now, you have to recollect what the formula for Ks there. So we cannot use the last formula. Last formula is restrictedly applicable for two conductors. When there are three conductors, they once again, in no time, you have to recollect the formula correctly in the entrance exam hall. So what is the formula for effective thermal conductivity in a series combination of three conductors means L net. It starts with L net by K net in series. L net means total length. That means L1 plus L2 plus L3 divided by K net. That means Ks is equal to L1 by K1 plus L2 by K2 plus L3 by K3. Recollecting this formula is a must, to be frank. Okay, since all the three conductors are same there, so you know that all the three conductors of same length there, so each is equal to L. So as per the starting wordings itself, L1 is L2 is L3 is L. Similarly, same dimensions, A1 is A2 is A3 is A. Yeah. Now, L1 plus L2 plus L3 comes out to be 3L. So generally, many students unfortunately miss the 3 there. 3L divided by Ks. Okay, Ks is 0.27 is equal to L1 by K1. So L by K1. Okay, L by 3K plus L by 2K plus L by 6K. Okay, this L term get cancelled throughout. So this comes out to be 3 by 0.27 is, if you just take the LCM of all these things there, this comes out to be 1 by K. So this is 1 by K. Yeah, from these things, we are getting K as 0.27 divided by 3. That means 0.09 there. Okay, the proper SI units. Okay, so K is 0.09. This is given in CGS now. So calorie per centimeter per second per degree centigrade. This is in CGS system, CGS like units there, calorie per centimeter per second per degree centigrade. But this is not the answer. This is only K there, K. We want to know what is Kp in parallel combination. Yeah. So when the exam is of reasonably little bit of next level there, next level, this question may find its place there. So B part there. We want to know what is their effective thermal conductivity in parallel combination. What is the formula for effective thermal conductivity in parallel combination for any number of conductors? Means K1A1 plus K2A2 plus K3A3 divided by A1 plus A2 plus A3. Okay, now, you know, K1 comes out to be 3K. Okay, all of you know that A1 is A2 is A3 there. So A1 is A2 is A3. That comes a constant as A there. A can be taken outside. So K1 plus K2 plus K3. K1 plus K2 plus K3 means 3K plus 2K plus 6K. I repeat, here everywhere A term will be there. A we have taken common place. Yeah, divided by A1 plus A2 plus A3. A1 plus A2 plus A3 comes out to be 3A. A term get cancelled. So this comes out to be 11 by 3 into K. If you just simplify it, 11 by 3 into K. So this is 11 by 3 into 0.09. So this comes out to be 0.33. So what is the unit given? Same unit you need to reproduce. Calorie per centimeter per second per degree centigrade. So this will be the answer for the question. Okay. Now, to save our time there, question answer, both are being pasted there so that we can be reasonably fast. Perhaps one of the model that is who often came in the entrance examination there many times. Okay, yeah. Two metallic rods are of same area, cross section area is same, but of different thermal conductivities, 4K and 6K. Okay, conductivities are given 4K and 3K, 4K and 3K, and the lengths are given as 2L and 3L. If the outer ends of shorter and longer rods are maintained at temperatures 130 and minus 20 degrees centigrade. Okay, we need to be slightly careful. Outer ends of the shorter and longer rods there. So first we have to see which is the shorter rod, naturally 2L length. The outer end means this one. The outer end of the shorter rod is maintained at 130 and that of the longer rod is maintained at minus 20. Then I want to know what is the temperature of the junction there. The two, understood. All these corresponds to thermal steady state there. What is the temperature of the junction in thermal steady state? A good examiner will use that one. And generally, that point is being skipped there, but understood, thermal steady state. Okay, pay attention. Now, the moment you hear that these two conductors are connected in series, first and foremost point is that the heat current will remain constant. Already we discussed in the theory, the rate of flow of heat will be same. Heat current is same, just like current electricity. In series combination, current is constant. What is the formula for heat current? Heat current is rate of flow of the heat energy, Q by T. Q by T means Ka delta theta by L. Now you ask yourself, what are the further constants there? What are the further constants in that equation? You know that all the three conductors are of same area mentioned. So this area is also constant. We are rounding it off. What does it mean? Ka delta theta by L is constant, out of which area is again constant. So it says that K delta theta by L is constant. So this constant by area constant will give you one more constant. So K delta theta by L is constant. You know, when PV is constant, we write P1 V1 is P2 V2. Similarly, when K delta theta by L is constant, K1 delta theta 1 by L1 is K2 delta theta 2 by L2. Okay, what is delta theta? As you know, higher temperature minus lower temperature. It's time for you to decide simply which is higher, which is lower. So all of you know, this is theta high, this is low there, and this will be intermediate. Okay, Now, for the first rod, K1 delta theta 1 by L1 means K1 you know 4K, length L1 you know 2L, but you have to be a little bit careful in writing delta theta 1. Delta theta 1 means high minus low. You know, that like this temperature is decreasing, like this temperature is decreasing. High minus low means 130 minus theta of the junction. Okay, theta of the junction, if you call it as x there, x. So we have written here x there, x, 130 minus x. Similarly, K2, L2 you can write. Delta theta 2 means is once again high minus low. Like this temperature is decreasing. Na? So this is high, this is low. Little bit of care you have to take is x minus of minus 20. Okay, not x minus of minus 20. That's the only care to be taken to get a very happy plus 4 marks. So x minus of this one. So intentionally I am highlighting with this color there. X plus 20 you get. X minus of minus 20, x plus 20. Rest of the things is a simple arithmetic, as you know. You get the answer like this. In the entrance exam, they may twist there. Instead of asking this answer in degree centigrade, they may ask in Kelvin or some other temperature scale there. You need to be careful. For example, in Kelvin, add 273 for it. 353 Kelvin you get. The next bit. Yeah, it is once again little formula substitution, but a small mathematical formula from schooling we have to recollect. Okay, if that formula is recollected, very easy bit. By chance that formula we don't revise, then yeah. So the first thing is that n number of conductors there of a same length, but coefficient of thermal conductivity is given k, 4k, 9k, 16k up to n square k. So I can make a note that they are going in a one rhythmic way. One is k, first one is 1k, second one is 2 square k, 3 square k, 4 square k, and finally n square k. So n number of conductors of different k's. So all those k1, k2, k3, k4, all these are given, and areas are given A, 2A, 3A, 4A up to NA. They are connected in parallel. Make a note that they are in parallel. What is the effective coefficient of thermal conductivity in their parallel combination? So you know that Kp comes out to be this simple formula. Whatever K1, A1 are given, you just substitute. K1 is K, A1 is A. K2 is 4K, A2 is 2A, and so on. If you just multiply these terms and write Ka plus 8Ka plus 27Ka up to n cube Ka. What is common means Ka common. Is here Ka is common, this highlighted one Ka is common, into 1 plus 8 plus 27 up to n cube. Here A common, 1 plus 2 plus 3 up to n. So A get cancelled, K will remain. The only thing is how we simplify it. Such questions are very common in different chapters of physics there. Many chapters we get it. Okay. 1 is 1 cube, 8 is 2 cube, 27 is 3 cube, this is n cube. 1 plus 2 plus 3n. 1 cube plus 2 cube plus 3 cube plus n cube. You have to be good at this list there. 1 cube plus 2 cube plus 3 cube is n into n plus 1 by 2 whole square. 1 plus 2 plus 3 up to n into n plus 1 by 2. So this term and this term will get cancelled. You are left with k into n plus 1 by 2. Okay, not just in one topic there. In several chapters, we have to use the knowledge of this particular point there. So we need to have respect and interest for it, just like we value the other things in physics. Okay, it is a common question of both NEET as well as JEE mains. That means as it is question matching, a little rare there, and this is the one. Okay, here this question is slightly different to our previous approach here. At the beginning of the class, we were discussing something like thermal resistance, thermal conductance there. There comes another important thing, Ohm's law. Ohm's law we definitely use in current electricity there too frequently. But here is a little bit of Ohm's law point we have to use. What is the Ohm's law in current electricity teaches us means current, okay, V is equal to IR as you know in current electricity, and current, that means electric current is V by R. Here V means potential difference divided by electrical resistance. That's what we know in current electricity in Ohm's law right from schooling. Okay, now just like electric current flow because of potential difference, heat current flow because of temperature difference. Okay, electric current flows because of potential difference and heat current flows because of temperature difference. So the same Ohm's law is applicable in the transmission of heat there. I is equal to V by R, where in current electricity V means potential difference. Here V means temperature difference. Here it is electrical resistance. This is thermal resistance. Symbol is same, but wordings are different. So I is equal to, instead of potential difference, temperature difference. Instead of electrical resistance, thermal resistance, denoted by the same symbol R. Okay, I is equal to delta theta by R. If you use this particular point there, the solution will be slightly comfortable. Okay, then say. So first of all, these two conductors are connected like this. Okay, these two conductors are connected like this. Then let us say that this is a higher temperature, this is a lower temperature. This is a higher temperature, this is a lower temperature. Okay, then heat energy or heat current flow from higher temperature, low temperature will go like this. So since the same current is flowing like this, these two are connected in series. These two are in series. So this is a higher, this is a lower. So heat energy enter from higher temperature comes out through the lower temperature. The same heat current will be flowing. Okay, pay attention. Okay, in this regard there, let me just tell you the other point there. By chance, the same setup is like this, and this is higher, and this happens to be lower. Okay, then whatever heat energy come, it will divide like this, and these two are said to be connected in parallel. But make a note that these two conductors are kept like this. This is higher, this is lower. Whatever heat current enters here, same current will go to the other end there. So these two are in series. Okay, in this particular series combination, the moment you recollect that it is series there, then the heat current will remain same. Yes, in series combination, heat current is same. I1 is I2. What is the formula for heat current we have seen? Delta theta by R. So I1 is I2, delta theta 1 by R1 is delta theta 2 by R2. What is delta theta? Higher temperature minus lower temperature. Okay, suppose you assume that this is higher there. So higher minus lower. Like this, temperature is decreasing, higher minus lower, theta 1 minus theta for the first one. Here temperature difference is theta minus theta 2, theta minus theta 2. Okay, let me tell you one point there. If somebody asks there, who said that this is higher temperature there? Yes, no one said. It's not given anywhere. That's an assumption. But please make a note that your end answer will never depend upon your assumption there. Whether you assume this higher, this lower, or vice versa. The end result will be one and the same. In such situation, they don't specifically mention which is higher, which is lower. Okay, just assume. Just comfortably assume this is higher, this is lower there. Then the only thing is about temperature difference, high minus low, theta 1 minus theta, and this is theta minus theta 2 by R1, R2. Remaining things is cross multiplication and doing simplification. That is straightforward thing. You will get that answer. Okay. The next bit. Oh my God. So intentionally I have written place, very important. Okay. Then many times entrance exam questions, this particular model. Okay, generally we do the question with the same length and same dimension there, same length and same area, but intentionally dimensions are slightly altered, and even the temperature intentionally given, instead of a happy 100 there, happy rounded 100, I have given 101. So no one should get irritation to say that 101 degrees centigrade there. Actually, that 101 only is a better value for this particular question. Okay, then say. So there are three conductors arranged in the form of a Y shape. They have got a coefficient of thermal conductivity K, 2K, 3K. Let me call it as number 1 conductor. This is 2, this is 3. These are having a K. This is first, second, third. Their Ks are like this, lengths like this, areas like this. Okay. Now, this end is at 101, this end is at 20, this end is at 0. I want to know what is the temperature of this particular junction. This is the junction, as you know. What is the temperature of the junction? Very similar question is there under the heading of same Ohm's law and so on in current electricity. In both the chapters, it is important. Okay. Now, the first point here is that, see, heat energy has a habit of going from higher temperature to lower temperature. You ask, he himself has given clearly 101 is a pretty high temperature here. Okay. So in the previous question, we assumed something is higher, lower. Here, he himself has given happy. So heat energy will go from a higher temperature to lower temperature. So this is the way the heat energy is going like this, or heat current we can say directly. Let us say this is a heat current I1. Whatever current I1 comes, here at this junction, the current will divide into two parts, I2 and I3. Whatever heat current comes, I2 here, I3 here. Now, as per Kirchhoff's first law, is the incoming heat current at this junction is outgoing heat. So I1 is equal to I2 plus I3. Okay, already you are well versed with I there. So I comes out to be Q by T into Ka delta theta by L. Okay, I is equal to Q by T into Ka delta theta by L. Here, practically none is constant. K is different, A area different, delta theta different, L different. So nothing is constant. So I1 means K1, A1, delta theta by L1, and similarly I2 and I3. What is our next step there? With enough patience and concentration, you have to write the corresponding values there. For the first conductor, K1 is nothing but K there. Area is A. Delta theta 101 minus X there. Delta theta means higher temperature minus lower temperature. All of you know, the heat current is going like this. Naturally, it flows from high temperature 101 to low temperature X. High to low, 101 minus X, divided by the corresponding length L is equal to K2. Concentrate on the second conductor. K2, it comes out to be 2K. Its area A by 2. In the temperature difference, current is going like this, high to low. So X is high, current is going like this. X is high, 20 is low. So X minus 20 divided by its length. Its length is 12 plus heat energy. Heat current is going from high to low. Okay. So K3 comes out to be 3K into its area there. Area is 3A. So under the exam tension conditions, you have to look fractions of seconds you get to look at the value there. Okay. I may be taking my own time there, but you have to be fast in the exam. So correctly you have to catch it and write it, please. Okay. 3K. A3 is nothing but 3A. Delta theta 3 comes out to be X minus 0. Okay. This is X minus 0 there. Whole upon corresponding length we have to write. What the length means L. Okay. Now, this K by L is common throughout there. This K by L is common there. So naturally, Ka by L will get cancelled throughout. Of course, this two will also get cancelled. So here comes the point that this is 101 minus X is equal to 101 minus X is equal to X minus 20 divided by 2 plus 9X there. This comes out to be 9X. You just solve this equation there. You get very comfortable value of X there. You'll be getting a quite comfortable value of X there. Yeah, 11 degrees centigrade will be getting. Just simplify it and just test yourself. Have the practice of that arithmetic, please. Yeah, cross-checking it, that one. Then the next point. Under the heading of the Stephen's law of heat radiation there, I feel that this is one reasonably basic and standard model. Radiation power of a sphere. When he says sphere, understood that it is a solid sphere there. So when we are saying that it is a sphere there, it is a solid sphere. Radiation power of a sphere is 64 watt. When it is maintained at minus 73 degrees centigrade. This is maintained at minus 73 degrees centigrade. So convert into Kelvin scale, add 273, 200 Kelvin. Its radiation power happens to be 64 watt. Now this particular sphere is cut into two parts. and you are changing the temperature. Temperature raised to 27 degrees centigrade, not raised by, raised to 27 degrees centigrade. So from minus 73, its temperature has become 27, nothing but 300 Kelvin. Now you want to know what is the radiation power there? Yeah. So over the years, these are the simple standards. Our exam is being conducted at. Then say, the only care you have to take from our side is that, you know, the Stephen's law of heat radiation. Stephen's law of heat radiation say that the radiation power, nothing but the quantity of heat energy radiated per unit time is given by radiation power. How much quantity of heat energy is being radiated out per unit time is given by sigma into surface area into temperature to the power of 4 into emissivity. E is the emissivity. So this temperature is to be expressed in Kelvin scale. That's why we have converted into Kelvin scale. Sigma is a constant value there. Okay, sigma is a constant value, as you know, 5.67 into 10 to the power of minus 8 watt per meter square per Kelvin to the power of 4. So that sigma value here we need not use, but you have to remember. So sigma is constant. For a given material with the same surface finish, emissivity is constant. So the radiation power is proportional to surface area into temperature to the power of 4. Now the thing is how to calculate the surface area. Okay, what is the surface area of a sphere means? In surface tension topic we get, in electrostatics we get, many times we get moment of inertia topics and so on. Surface area of a sphere is 4 pi r square. What about the surface area of the hemisphere after it is being cut into 2 parts? That surface area includes area of this one plus area of this circular part also. All of you know this full surface area is 4 pi r square. Area of this one will become 2 pi r square. This circle having an area pi r square. So this surface area is 3 pi r square. So this surface area comes out to be 3 pi r square. Okay, 2 pi r square for this curved surface area. For the circular area, pi r square, 3 pi r square. I want to know what is the power there. Already we have ended with the power is proportional to surface area and temperature over 4. You want P2 now? So start with P2. P2 by P1 is SA2 by SA1 into T2 by T1 whole to the power of 4. You should not forget 4. You should not forget 4 whole to the power of 4. So P2 by P1 is nothing but 64 watt. Initial surface area 4 pi r square, final surface area 3 pi r square. SA2 by SA1 means 3 by 4. Temperatures, you know, directly use the values there. Do a little bit of arithmetic, you get this power there. Okay. Yeah. This is a question involving, it appears to be of a little bit of too much of data there, but you need to be careful. Okay. So exam may be slightly tougher, not too much tougher there, never too much tougher. Okay. And the lengthiness and a little bit of long data is there in the question. Ratio between lens, radii, and emissivities and radiation powers of two filaments of a bulb are given there. Okay, all of you know, in the regular bulbs, the filament will be there, tungsten filament. The ratio between the lens, radii, emissivities, and radiation powers of the two bulbs are given. So you have to just dump the data here, there, whatever data is given. And temperature of first filament is given as 327 degrees centigrade. I want temperature of the second filament. In the exam hall, you have to correctly catch. Is he asking the question answer in terms of centigrade or Kelvin? Yes, he has given in centigrade, asking the answer again in centigrade, but there is a little bit of care need to be taken. Okay, just now as we have seen, the radiation power is nothing but sigma into surface area into temperature to the power of 4 into emissivity. Okay, whenever you are comparing two things, there is comparison of two filaments. Ask what are the constant terms. Sigma is a constant. Okay, then the main point here is that how to calculate surface area. Yes, Stephen's law, the main wording is surface area. Surface area of a solid sphere we have seen, hemi-solid sphere we have seen. Now it is about a filament. So a filament is a long cylinder with a radius negligible there. Radius is negligible. The surface area of a filament is nothing but curved surface area of the filament there, nothing but 2 pi RL. Okay, whenever there is a filament of radius very small and length appreciable there, its a surface area is nothing but curved surface area of this one. We study in school there, curved surface area of a cylinder comes out to be 2 pi RL. That's the only point that will play the role. So power is this sigma constant can be replaced by proportionality sign. P is proportional to surface area 2 pi RL. That's the only point to be properly recollected. Temperature to the power of 4 into emissivity. Okay, now here the other point is that the emissivities are not same. They are of a different one. It is not the, okay, maybe tungsten filament, other one platinum, something like this. So their emissivities are not same. You have to catch it, that point there. The rest of the thing says, in this particular formula, 2 pi is a constant. P is proportion to RL T4E. Then you can just find out the ratio. First thing is, this temperature in degrees centigrade, you have to convert into Kelvin. You definitely get the answer in Kelvin again. But that Kelvin is to be reconverted into centigrade. From centigrade to, you have to come to Kelvin. Again, from Kelvin to centigrade place. Okay? That's the thing about this small thing. Okay, this is a standard question of Newton's law. Newton's law of cooling, many times there. So just our team is focusing it. Just practice this a simple bit there. Practice the bit so that we can enter into some questions of KTOG. Okay, kinetic theory of gases. Okay, very important and most fundamental and basic question. Simple bit. Okay, but simple bits also need practice, as you know. Okay, then we are just moving to, yeah. There is a statement in NCERT textbook there. No one can go to the sun there naturally. Yes. Then how do we measure the temperature of the sun? The two, by using Wien's law. Okay. Yeah. So how do you estimate the temperature of the sun using the Wien's law? Okay. All of you know that sun gives us the visible light, which is perfectly white. So sun emits white light, be pure, with a varying wavelengths, varying right from 3,800 angstroms to 7,200 angstroms. Now, sun may be giving variable wavelengths, but which color is to be taken as the mean color means the yellow there. Yellow is to be taken as the mean color, and its wavelength is to be taken as 5,800 angstroms. Sun may be giving different wavelengths, but which wavelength is the representative of sun's white light means the yellow color of wavelength this much. Convert angstroms to meters. Then you know Wien's law. Wien's law says that wavelength corresponding to the maximum spectral radiancy into T is equal to this one. Lambda m into T is a constant. What is the Wien's constant? You should be well aware of 2.9 into 10 to the power minus 3 meter Kelvin. So 2.9 into 10 to the power minus 3 meter Kelvin there. You know what is the wavelength here there and this one. So from this, you have to calculate the temperature of the sun. The temperature of the sun, you will get of the order of around 5,000 Kelvin. Yes, 5,000 Kelvin. Okay. Coming to the next bit. Yeah. This is also many times repeated version bit. Okay. The power radiated by a black body is P. The power radiated by a black body is P, and the wavelength corresponding to the maximum spectral radiance is lambda naught. So power radiated is P, and the wavelength corresponding to maximum spectral radiance is lambda naught. It is a very important question based on the Wien's law plus Stephen's law of radiation. A combination of two important subtopics of our physics. So, power radiated is P and lambda m1 is given. Now, its temperature is now changed so that maximum spectral radiancy corresponds to this much wavelength. Lambda 2 is given. Then you want to know when lambda is changing like this, how does the new power will become? Wavelength corresponding to maximum spectral radiancy changed from lambda naught to 3 lambda naught by 4. Then how does the radiant power change? Everyone in the class know that Weins law says that the product of lambda into T is constant. That means T is inversely proportional to lambda. Lambda changing doesn't mean that temperature is changing. Yes, lambda got changed. Temperature got changed. When temperature changes, the heat it radiates will be more. Yes, low temperature body, less heat radiation. High temperature body, more heat radiation. So you know that lambda is changing. So temperature does change there. I want to know how does corresponding power changes. So power is sigma surface area and temperature to the power of 4 into emissivity. By now we have noticed small formula. Okay, just you have to remember it and easily score the marks. So power is sigma into surface area into temperature to the power of 4 into emissivity. What are the constant terms in sigma? He is talking about the same body. Sigma constant, surface area constant, emissivity constant. From these things, P is proportional to T to the power of 4. Then, but T and lambda are inversely proportional. T and lambda are inversely proportional. So in place of T, 1 by lambda to the power of 4. So naturally, P2 by P1 means lambda 1 by lambda 2 whole to the power of 4. The rest of the things is simple substitution. Simple substitution, and happily you can get the answer. Yeah. Going to some slightly modified or changed questions. Keep in view the slightly tough exam being expected. They're slightly tough. Okay. Then it is something like this. In kinetic theory of gases, there RMS speed of oxygen molecules at 0 degrees centigrade is 480 root 2 meter per second. Here they have given a RMS speed of oxygen molecules. He is asking now average speed, not RMS speed there, average speed of different gas, hydrogen molecules at different temperatures. The two, instead of meter per second, they are asking in kilometer per second. So simple question only, but twisted different stages. Simple twist. The gas is changed, oxygen to hydrogen. Temperature change, 0 to 819 degrees centigrade. And unit we want is getting changed from meter per second to kilometer per second. And main thing is RMS speed and average speed. Okay, you should be a perfectionist with the formulae of most probable speed, RMS speed, and so on. Okay, the first gas we are talking about is O2 gas. Second one is hydrogen. You know the molecular weight. Molecular weight of hydrogen is 32 gram molecular weight. So 32. Hydrogen gas is 2. What are their temperatures given? 0 degrees centigrade and 819 degrees centigrade. So these are the temperatures given in centigrade converted into Kelvin. What is the main point there? What is the RMS speed of gas molecules of a gas? RMS speed comes out to be root 3 RT by M. First gas, na, subscript 1. R is a constant. R is a constant, 3 is a number there. Chod do. So RMS 1 is root 3 RT 1 by M1. What about the average speed of the hydrogen gas molecules? That formula you have to be good at. Okay, this is a slightly lengthy formula and we need to be focused at that formula. Root 8 RT2 by pi m. Okay, now comes the arithmetic part. Now comes the arithmetic part. RMS speed given, we want average speed. Just divide one with the other there. Okay, since we want the average speed there, better divide second with first. You want average speed, na? Whatever you want, better keep it in the numerator, please. So second by first. So here I am writing second by first will give you V average 2 by V RMS 1 means common number of you root 8 RT2 by pi M2. If you divide with this M1 by 3 RT1, divide one with the other. Okay, the R term get cancelled. Now, what is the RMS speed of the gas molecules given? 480 root 2 naturally in terms of meter per second. Now, doing this arithmetic is a little bit of art. Okay, accurately doing the two in time doing requires a little bit of 100% practice, please. Okay, root 8, R term get cancelled. What is the temperature of 819 degrees centigrade means 1092 Kelvin. This pi as it is. M2 comes out to be 2. M1, 32. 3. T1 means 273. Yeah, 273 and 1092 are little bit frightening numbers. Little frightening numbers. But 273 by 1092 is exactly 4 times. Precisely 4. Okay, so we average 2 by 480 root 2 is, come on, tell me, this is 4 now. Then you can see here, there. Here, you have to see the data given. Whether he gives or not, you can take it. Okay, pi is 3.14. Almost you can take it as 3. If the answers are not close by, when the answers are having sufficient gaps or between them, then pi, instead of 3.14, we can write 3 there. Okay, so this pi is 3 there. So we can see that this comes out to be, this 2 into 8 comes out to be 4 there. 2 into 8 is 4 there. You just do the necessary simplifications of these things. Then, or else what is being done here is whatever is being written here there. So whatever is being written, see here, it comes out to be. Okay, this is the way it is being written. Let me explain that way. Root 8 into 4, 32. Root 32 into 32 is 132. And a 1 time 32. Root 8 into 4, 32. 32 into 32 under root is 32. Divided by, this comes out to be pi. Pi is 3. 3 into 3 is, under root of 3 into 3, 3, root 2. Okay, this root 2 happily get cancelled. You can do the arithmetic by many methods. I'm just explaining the way it is being written here. The root 2 get cancelled. So V average 2 comes out to be, okay, this 3, 180, 480 is 160 times 32. You get this answer. This is the answer being expressed in meter per second, 5120 meter per second. I want the answer in kilometer per second there. So naturally it comes out to be 5.12 kilometer per second. Okay, intentionally I have done the arithmetic in front of you so that you also practice. Don't just think that we can do the arithmetic. Such a practice is a must for you to be speedy and accurate in the final exam. Okay. A gas has 6 molecules with the speeds 6, 8, 10, 10, 10 root 2 and 10 kilometer per second. So this is a gas with a limited number of molecules there. Okay, after all, it has 6 there with different speeds like this. Okay, the point number 1 we want is, what is the most probable speed of this gas having only 6 molecules? That is point number 1. That is being correlated with the next one. Find the temperature of a helium gas, that too in degrees centigrade, so that the root mean square speed of this helium gas is exactly 1 by 10 times the most probable speed of the above said gas. Okay, some gas is given. Now, I want to know what is the temperature of a helium gas so that its RMS speed is 1/10 of the above said gas. First of all, I want to know what is the most probable speed of the gas number 1 there being listed here. All of you should recollect the basic definition of most probable speed. Most probable speed is the speed possessed by most of the molecules of the gas. Most of the molecules of the gas. All of you know that 6 is the speed possessed by only one molecule. Only one molecule has 6. Only one more molecule, one has 8. Only one molecule has 8. Only one molecule has 10 root 2. One single molecule 6, only one molecule 8, one molecule 10 root 2. But 3 molecules have a speed of 10, 10, 10. 3 molecules have speed 10. The most probable speed is the speed possessed by most of the molecules. So 3 molecules possess the speed of 10. So the most probable speed happens to be a simple 10. But you have to be careful. That is in kilometer per second. Convert kilometer per second to meter per second. Convert kilometers to meter into the SI system. Okay, what is given in the second part of the question there? It is said that RMS speed of the helium gas is 1 by 10th of the most probable speed of the above gas there. Then with that, we want to know what is the temperature of helium gas, that too in degrees centigrade. What is the formula for RMS speed of the helium gas? Is root 3 RT by M. Okay, the helium gas is RMS speed is root 3 RT by M is 1/10th of the most probable speed, 10 to the power of 4. Then rest of the things are simple. Root 3 RT by M is 10 to the power of 4 by 10, 10 cube. Just square on either side there. 3 RT by M is 10 to the power of 6. One important point I want to mention there. Don't take R, capital R as 8.314 as it is there. Is 100% correct that universal gas constant is 8.314 joule per mole per Kelvin. But it is highly convenient to write it as 25/3 there. So if you write like this, your arithmetic will become easy. So you write R as 25/3 so that 3 happily get cancelled. Do the remaining simplification, very ordinary simplification that is. You get the temperature as 160 Kelvin. There will be a tempting answer as option 1, 160 degrees centigrade they give. So the answer is 160 Kelvin, Kelvin, Kelvin. But you want the answer in degrees centigrade, convert Kelvin to centigrade by subtracting 273. Okay, so the answer here comes out to be minus 113 degree centigrade there. So this is the answer for the question in terms of degree centigrade, minus 113 degrees centigrade. So I expect everyone doing enough good work from your end in all the subjects there. Okay, your total will depend upon the subjects. Once the papers are slightly on tougher side, every question, every 4 marks you get is a very, very costly and important thing there. So keep in view the increased competition for this exam there. Okay, definitely more days means more will be the competition there. Keep that point in mind, and I'm sure you work hard and definitely do well. All the best, my dear students. Bye-bye.